Hello everyone, this is Dr. Hopkins recording another video for Chem 472, and today we're going to continue exploring, at least in much more depth, the first law of thermodynamics. Alright, so first law of thermodynamics, this is a slide you've seen in the last two videos when we were talking about both heat and work, but in this case we're going to focus on the total internal energy change. And I've also added an additional definition based on the idea the first law of thermodynamics prevents a perpetual motion machine, if you will. Okay, so we go to internal energy. U is what we're going to use. Sometimes you'll see some textbooks will use E. I tend to use U. I think your textbook uses U as well for your internal energy. So the absolute internal energy, if we were to figure out all of the nuclear forces that are binding all the mass together and so forth, we could calculate an internal energy for any particular molecule or atom. But we're not interested in the absolute internal energy. We're not physicists. What we're interested in is chemical change or processes, and so we're going to look at changes in internal energy. So that would be the differential of U, so du. Now, internal energy change is the first of our state functions we're going to define. Okay, so a state function is an exact differential, one of those things we talked about in the math video. And in a state function, if you have a cyclic process, so if you start at state 1 and you end at state 1, so a cyclic integral, if you evaluate that integral, which is delta U cyclic, it's 0 because you've essentially done nothing, right? So as opposed to work and heat, the path matters. In internal energy change, it depends on where you start and where you end. Doesn't matter how you get there, okay? And so if we have a cyclic process, the internal energy change is 0. And so that means our heat and work are equal, but they're opposite in sign, right? So what that basically tells us is that the work done, any kind of work done in that process, is paid for by the heat added to the system. So we can add heat to do work, or likewise the other way around. Okay, so if we go explore a little bit more internal energy changes, is one of the things that's elegant about thermodynamics is that we have some sets of equations, we have some conditions under which we do processes, and then we can manipulate those equations and derive what we need. Anyway, we start with the statement of the first law. Okay, so in terms of heat and work, we can also, as with any state function, expand the differential in terms of variables. In this case, we've chosen t and v, right? So we have a partial u, partial t, a constant v, and so forth, right? In the last video, we learned that the heat capacity at constant volume is the same as this partial derivative, right? And I also note here, and this is important to understand, that the heat capacity at constant volume is a fact. It's a number. It doesn't matter whether you're doing things at constant volume or not. You can still use this heat capacity, right? And so we can substitute that in for our first term, and we get CV dt. And then we have the second term is the partial u with partial v at constant t. So that means how does the internal energy change as we change volume? Holding temperature constant. And if we are considering an ideal gas, that term is equal to 0, right? Because there's no intermolecular interaction. So if you change the volume, if there's no intermolecular interactions, it doesn't really matter whether you're pulling them apart, right? Because you're not breaking any intermolecular interactions, you're not forming any intermolecular interactions, and if temperature's not changing, there's no change in internal energy. It's also important, I put down here at the bottom, that if we were to call this work, which is minus PdV, this is not equivalent to minus P in all cases. Okay, so that's the internal energy change. So those are a couple of expressions for internal energy that we will use as we go through. We are also going to define a new state function. Okay, so internal energy change, or internal energy, we can define based on physics. Enthalpy, we're going to set a definition. So we're going to define this new state function H, and it's going to be U plus PV. And we know it's a state function because all of the components are state functions, so it's an exact differential. The cyclic integral is 0. So once again, it all depends on where you start and where you end. And so if we were to evaluate, remember, we're interested in processes, we're interested in change in chemistry, so we're not going to evaluate the absolute enthalpy, we're going to evaluate the change in enthalpy. So dH, so we take the derivative throughout, and you end up with du plus pdv plus v dp. Okay. Now we can also insert the statement of the first law in for du, so we dq plus dw plus pdv plus v dp, right? So we're expanding out once again. This is kind of the elegance of it. Let's say we're in a process that's constant pressure. Okay, so that means this term drops out, dp go to 0, so we're left with these three terms. And then let's consider only PV work. So we're not going to worry about any electromotive or surface tension work, just PV work. We're talking about gases, right? So we can substitute in minus PD for dW, minus PdV. And so minus PdV plus PdV goes to 0, and we're left with heat. So enthalpy is basically the heat at constant pressure. Okay, so this is one of the reasons why when we talk about enthalpy change in Gen Chem, you often said the heat of a reaction. It's not just the enthalpy of a reaction. We use those interchangeably, and that's partly because most chemistry we're doing in atmospheric pressure, which is constant pressure. So this is part of the reason why we defined enthalpy, is that the natural variables for enthalpy are P and T, not V and T like they are for internal energy. Anyway, so enthalpy, we can once again use this to define a heat capacity at constant pressure. Here we just hold the heat capacity at constant pressure. This is dq over dt. Well, we just showed that at constant pressure dq and dH are the same, so that this partial derivative is Cp. Okay, so as opposed to Cv, which was related to internal energy change, this is Cp related to the enthalpy change. We apply our equipartition theorem, so we apply um plus 3/2 RT to U for a monatomic ideal gas. We could apply that for any of them, but we're going to just do the simplest case. And so we substitute that in. We got plus PVM. Now I've switched to molar volumes. I apologize, but if we're if that's PVM for an ideal gas, then PVM or PV is equal to nRT. PVM is equal to RT. So that means that it's just this internal energy at 0 Kelvin plus 5/2 RT. So our Cp is 5/2. So you'll also notice, right, so our Cv in that case was 3/2 R. And this holds regardless of whether we're monatomic, diatomic, or polyatomic. Cp is always greater than Cv. And the reason for that is that under constant pressure conditions, some of the heat that goes in can be stored as work, PV work, and not raise the temperature. As opposed to at constant volume, since you have your dV is equal to 0, you can't do any work. So Cp is always greater than Cv because you can do work in that sense. Okay. So then we have more of the elegance of thermodynamics. So dH is du plus pdv, the definition of the differential. Like I said earlier on the previous slide, we can expand H in terms of T and P. Okay, we just defined this to be Cp, so we would substitute then, and that's Cp dt. And then we have the second parameter, or partial derivative, dH dP at constant T. Okay, and now for an ideal gas, I'm not really going to prove this as much, but for much the same reason that the partial derivative of U with respect to V at constant T was equal to 0, this term is also 0. So for an ideal gas, the enthalpy change is just Cp dt. And so we're going to use these kinds of manipulations of internal energy and enthalpy that we've talked about in this video throughout the rest of our discussion of first law, and we'll apply it to various processes. And so depending on how you do a process, depends on which one you want to use or how you want to use it, or whatever is natural. Right? So constant pressure, dH, is really important in terms of the heat. Constant volume, du, is important because it's the heat, and so forth. So we'll explore that a little bit more. But until next time.